Infrared spectroscopy gives us information about what functional groups are present in a molecule and what ones are absent. Now, how cool is that? In terms of discovering what the exact structure of a compound is, of course, it's critical to know the functional groups. So it's extremely useful to put a sample in an IR spectrometer and get a spectrum out that gives you information about the functional groups. How in the world would that work? Well, I can give you a short version of the explanation that probably will satisfy. If you want to know more, there are lots of descriptions in textbooks about how IR works. But a simple version that helps us understand what we need to know is based on what we know about the behavior of springs. You might have taken some physics and understand that already, but let's just take a little bit of a look at how springs behave. So let's say we've got a spring like this, and we stretch that spring. So we're going to start with something like that, and we'll stretch it. Now there's tension, and it would like to go back where it was. Only when it does that, it will overshoot and actually compress. And since it's compressed, now it wants to expand. And if the energetics are just right, that expansion is going to take it to look back again like this. And so we set up a vibration. If, like they do in physics, we use a spring that has no friction, this vibration can go on indefinitely. We've given the spring some energy by stretching it. It compresses, it restretches, it will compress again and restretch. This is simply vibration. And the vibration occurs because we've stretched provide energy. Now, of course, for a strong spring, we won't be able to stretch it as much for a certain amount of energy, and for a weak spring, we'll stretch it more. So the stretching, as a result of putting in energy, depends on the strength of the spring. So that's one of the variables that determines the vibration. Picture another one. Let's say that the spring has little weights on it. Because those weights are small, it won't affect the frequency of that vibration very much, will it? That vibration will go on about the same as it was before because those weights don't have much effect on it. On the other hand, when we compare that to a situation where we put very large weights on a spring, now we could guess that it will take a lot of work for that spring to move those big weights. And as a result, the vibration will happen much slower. So the weights affect the vibration frequency So we have two things. The strength of the spring is important, and the weights at the end are important. And those two things will affect the vibration frequency. That's key. Because what we're going to be measuring in IR spectroscopy is the frequency of vibrations caused by absorption of energy, just like this spring. But before we get there, I want to point out that this isn't the only kind of vibration we could imagine for this spring. Let's look at another example. Let's take a spring has some weights on the ends. It's poised vertically, and we move it so that it's bent off to one side. Now, it will want to go back where it came from, but when it does that, it will go too far. And of course, since it's too far, it will go back where it came from. Only it will go too far again, so it goes like this and back and forth. So there's a second kind of vibration that we could be talking about. It's sort of a wagging kind of vibration. And both of these kinds of vibrations happen when you shine a certain wavelength of light onto an organic molecule. Because both of these types of vibrations can be occurring simultaneously, IR spectra can be a bit complicated. Let's take a look at a spectrum. Before we look at an actual spectrum, let's talk about the axes of IR spectrum as it's printed from the machine. And notice that this is transmittance, which means when there's no absorption, this is transmittance, which means then no energy is being absorbed. There'll be 100% transmittance. Nothing is happening. It's way up here. When energy is absorbed, we'll see a change in the spectrum like this. And then as we change the frequency, when it's not absorbed anymore, it'll go back up here. So one thing is, here's where the action is. And what we read is the frequency in reciprocal centimeters of that absorption. Energy is being absorbed when we see a peak going down. When something sees something up here, no energy is being absorbed. We're particularly interested in the frequency of that absorption. Now, what we said is, when we looked at springs, the frequency of absorption was dependent on the strength of the spring and the weights at the ends. In organic molecules, the spring is the bond between two atoms. And the variable that's important is bond strength. The weights are the atoms. And the weights vary depending on the element. So what elements are held together by which bond, how strong it is, determines the frequency of a vibration that results from absorption of light. The frequency of vibration is printed here. And so what we see as a specific frequency which tells us which atoms it is that are attached to by the bond, and what kind of bond it is, how strong the bond is, single bond, double bond, triple bond, between which two atoms. That's exactly what functional groups are. Functional groups are determined by which two atoms are held together by what kind of bond. And that's why infrared spectroscopy tells us specifically what functional groups are present or absent. It's because the bond strength and the weights of the atoms are the two things that are determining the frequency that results from the absorption of infrared light. Now let me tell you a couple things about the spectrum itself. There are two main regions in an IR spectrum. The one that starts right about 4,000 and goes down to almost 1,500. And a second one that starts pretty much at 1,500 and goes all the way down to 500, 400, the rest of the spectrum. These two regions are really very different from each other. And by the way, when you notice this axis, do you see something interesting? That this is not a linear axis, that the marks actually get further apart as we go from left to right. That's because we're plotting frequency here, reciprocal centimeters. But these two regions that I was talking about give you distinctly different information. The one on the left, from 4,000 to close to 1,500, tells you information about specific functional groups. Of course, that's highly useful. The second region provides a molecule-specific pattern. In the first region, we're going to see only a few peaks. Very specific locations. When we get to the second region, the pattern is very much more complex. These specific absorptions in the left-hand region come at frequencies that are distinctly characteristic of certain functional groups. And so we can look up in a table the specific frequencies where we see absorptions, and it will tell us what kind of bonds are likely causing those absorptions. On the other hand, the region on the right is a complex pattern, and it's typically pretty difficult to interpret in terms of specific functional group atom bond absorptions. But rather it has a distinctly different use. This is called the fingerprint region. And this region functions just like fingerprints for people. No two different structures have the exact same fingerprint region. So if you think you know the structure of a compound, and you find in the table of spectra of compounds that exact structure, you can compare the fingerprint regions, and if they're the same, then that is the structure. So this pattern has the potential of proof positive identification of a structure, or on the other side of the coin, proving that two structures are different. That won't tell you what it is, but it will tell you these two structures are not the same if they don't have the same fingerprint region. So this is a very useful region in terms of structure identification, even though it doesn't tell us much, really, about the specific functional groups. On the other hand, that region on the left does tell us quite a bit about functional groups. And let me give you a brief summary of what we gain. You can look in tables and see specifically where one would expect certain functional groups to absorb. I'm going to give you some general information. Up in this region, we expect to see NH. We expect to see OH. We may be able to distinguish between these two, but it isn't always so simple. In a region adjacent to that, around 3,000 and in the upper 2,000s, we'll see a variety of CH absorptions. And just exactly where this comes depends, among other things, on the hybridization of carbon. Moving further to the right, in this region, we'll see a triple bond, if it's present, between two carbon atoms, between carbon and nitrogen. They come in a similar region. That's not too surprising. The carbon and nitrogen weights are similar. The triple bond strengths are similar. And then finally, in the region that's in the roughly 1800 to 1600, a variety of carbonyl functional groups appear. And you may get some very specific information about which carbonyl-based functional group we're talking about, depending on where it comes. But other structural features in the molecule can move those absorptions around, so it's a little bit tricky to say exactly which carbonyl functional group you have. So here it is. There's a specific functional group region on the left, and in these very specific portions of the region, we can see NH or OH, CH, triple bonds, and carbonyl, all separated from each other. So that's extremely helpful. If there's no absorption in any one of these particular regions, or several of them, those functional groups are absent. If there is absorption, those functional groups are present. And then, of course, we have the fingerprint region, a complicated pattern that is molecule-specific, that lets you, like fingerprints for people, say yes or no to whether two samples have the same structure or not. Now, finally, I thought you might want to see a specific actual spectrum. So I have one here, taken from a database that's kept in Japan, the SDBS database that is extremely useful, widely used by many. Very easy to find on the web. And take a look at this spectrum as illustrating what I was just talking about. There is little absorption in this region, no NH, no OH. This absorption occurs in the range for CH, so we know CH is present. In this range where we expect to see absorption for triple bonds, absorption is absent. So we can say there's no alkyne, no nitrile. And then finally, we see a strong absorption in the range where we predict carbonyls will absorb. And by the way, carbonyl absorptions are almost always strong and sharp, as you see here. Ultimately then, on the right, we see a complicated pattern that will be very difficult to interpret. It's the fingerprint region. And it will let us determine whether our sample is exactly the same structure as some other sample. Perhaps because we're matching spectra from a database like this one. Now, this doesn't tell us what structure it is, does it? Unless we guess correctly and find the fingerprint match in a database. But it does tell us quite a bit about the structure. There's no NH functional group. There's no OH functional group. There is CH. There almost always is. There are no triple bonds. But there is carbonyl. So we know quite a bit about the structure. And then we can move on to get additional information from other instrumental techniques to help nail down the exact structure.